Okay, so last time we started talking about types of reactions, and again, a reminder that we have basically two classifications of reactions. Our sort of big classifications being double displacement, and with double displacement, again, we have two ionic compounds. Again, making new ionic compounds on the other side here. And in this case, a more specific classification can be a precipitation reaction. And that's when one of these guys obviously forms a solid. And we talked about solubility rules as a way that we could use to determine, for example, what will form the solid and if a solid at all would form. Remember that if things are soluble based on the solubility rules, those things are not going to form a solid and they will basically make a solution which is aqueous. If they are insoluble, they will make it precipitate, and those are the guys that get the solid symbol next to them based on those solubility rules. Remember, there are some rules of things that are soluble. And if they do not have exceptions, for example, like sodium or things from group one, as soon as you see those in an ionic compound sort of formula, you know that that should be soluble and make a solution and be aqueous. There are some, for example, like chloride, which is soluble in pretty much everything except for three sort of exceptions: lead, silver, or mercury, which would then make it insoluble. So there are a few different rules we could use for that. As we'll talk about here today as well, acid-base reactions also fall under the more specific classification of double displacement. The sort of other big category of reactions are redox reactions, and redox reactions basically involve electrons being transferred. And under here, we have a lot of more specific classifications, like, again, synthesis reactions, single replacement reactions, combustion reactions, and decomposition reactions. And we're going to get into those obviously today. We got into a little bit of it obviously when we talked about balancing redox reactions last time as well. When we look at a double displacement reaction, there's three types of, or just in general, there's three types of equations that we come across. We have the molecular equation, which basically shows us everything as they are reacting. So again, if we had sodium chloride, which would be aqueous, plus some silver nitrate, which would also be aqueous because it has nitrate. That's going to be a double displacement reaction. Again, positive, negative, switching partners makes a little sodium nitrate, which will be aqueous, and silver chloride, which is an exception and will make a solid in this case. And that's the molecular equation. We write out everything just like normal. Yeah. So it should be the one we were doing last time as well. So here we have the molecular equation. We could write a total ionic equation, which shows anything that's a strong electrolyte will break apart, like the sodium, and the chloride would break apart. The silver and the nitrate would break apart. The sodium and the nitrate on the other side would break apart. And since I'm running out of room, I'm running into my thing, I'll go underneath it, plus our silver chloride, which is a solid. So this type of equation is what is referred to as the total ionic equation, or net ionic equation, or not net ionic equation, total ionic equation, or complete ionic equation. And in this case, we break up everything that's a strong electrolyte. The only things that we really do not break up is anything that's a weak electrolyte, we keep it together. Anything that's a solid liquid typically keeps together. And also, for example, a lot of times gases, which are covalently together, we don't break apart. But once we get to the total ionic equation, we can again look on each side of the arrow and we'll find ions that are exactly the same. So not different, not attached to anything, but looking exactly the same. And those are spectator ions. And they are just hanging out watching, so they cancel out. And that leaves the, I'll come up here, our net ionic equation, which really tells you sort of what is happening in this case, which is the silver plus the chloride are coming together to make that silver chloride solid, and that's our net ionic equation. And again, it basically is 100%, sort of what is happening in that particular reaction. Any questions on that stuff there? All right, so last time we were talking about solubility rules, and we went over some examples as we just talked about there, and I just pretty much did this example here. We want to write a balanced molecular equation. Remember that if you are predicting sort of what's happening on the product side, you want to make sure you get the right formulas down first, right? And then you want to balance the equation. Again, try not to do those together. If you have a strong electrolyte, going to completely break apart into ions. You're going to find your spectator ions like we just did there and cancel it out. And actually, this example is the one I just did there on the previous page or slide. And so we won't look at that one. We'll take a look at this one. So why don't you try this one here? Write the equation for the precipitation reaction between aqueous potassium carbonate and aqueous nickel 2 chloride. So why don't you write all those equations, the molecular equation, total ionic equation, net ionic equation, and why don't you also figure out the spectator ions. So take a few moments there and see formulas down first before we put what's on the product side. So again, the basic unit here is K plus and CO3 2 minus, and the basic unit here for our second guy is nickel with a +2 charge and Cl minus. So those are the basic ions that are going to switch partners. That means when I put together the K plus and the Cl minus, I do get KCl, not K2Cl2, because that's not so good. And here I get nickel and carbonate coming together. +2 -2 gives me NiCO3. And I'm imagining that might be my precipitation here, as potassium is definitely soluble in everything. Question? We'll see in a second, but they most likely will be, yes. No. Yep. So we got our molecular equation here, which is what we're looking for, and we now can balance it now that we have all the right formulas. So maybe a 2 there, and I think that might be it. So this is our molecular equation here. And if we want to write our total ionic equation, we're going to break apart anything that is a strong electrolyte. So this will give us 2 potassium ions. Again, the 2 comes to the front and will give us a carbonate ion. The nickel 2 chloride will also break apart into nickel with a +2 charge, and we will get 2 Cl minuses in this case. Again, this 2 comes to the front of the Cl. On the other side, we get 2 K pluses as that 2 gets distributed to both, and we will get 2 chlorides, and in this case here, our solid will stay together. And that would be our total ionic equation. We can now find our spectator ions, and as was mentioned, what we're really looking for is ions on both sides that are exactly the same. So we got 2 potassiums there, and we got 2 chlorides there, and 2 chlorides there. So those guys there would be our spectator ions, and they should be the exact same amount on both sides, and they should be the exact same thing on both sides there. And with those spectator ions, we're just going to cross them out here, and this is going to leave us our net ionic equation, pretty much what's left. So our net ionic equation here would be our nickel. It's going to come together with our carbonate, and we're going to make a little nickel 2 carbonate over here, and that would be our net ionic equation. So a reminder that when you write these equations, anything that's an ion does need to have a charge written with it. Any questions on that there? So ultimately what's happening in this reaction is that nickel and the carbonates are coming together to basically form that solid which comes out. Remember, forming a solid is one of the 3 reasons why a reaction takes place. So ultimately this is sort of what's happening. Question either? They do not. Really, what's happening in this case is if you just take all your ions, which are these four basically up here, right? And this is what you got floating around, right? So you got this floating around, you got some carbonate floating around, you got some nickel 2 floating around, and you got some chloride floating around. What happens though is these two guys will be attracted to each other and they'll come together and precipitate out. The remaining spectator ions are just floating around, having a good time. Yeah, hanging out on the pool, not doing too much. Yeah, so they're just floating around. Yeah. Question? Yeah, typically you should probably include the states with it as well as the charges for sure. So very common error people make on these is they write these equations and these ions and they don't put charges for sure. But you should probably also include the states as well. Other questions? Yeah, that was that one. That was that one still. All right, so why don't we try these two here? So predict the products, balance it, and why don't you write the other equations too, the total ionic, net ionic, and all that. Okay, so let's take a look, see how you're doing. Start with the first one. So again, definitely want to make sure correct formulas first before we worry about the balancing, if there is a need to. We definitely know this is a double displacement. This is the only reaction where we basically have two ionic compounds coming together. So again, basic unit here, K plus and Cl minus, basic unit, silver plus 1 and nitrate minus 1. So switching partners, that is +1 and -1, which will give me KNO3. That has nitrate in it, so I know it is soluble. Uh, Switching the other partners there, that's silver with a +1 and chloride with a -1. So again, when I put that together, I get AgCl. Remembering our solubility rules, chloride is soluble in everything except for silver, lead, and mercury, which means this then would be insoluble and we would get a solid in this case. Now that I got the formulas down correctly, we want to make sure it's properly balanced. And in this case, it looks like we're good. We're actually balanced, I believe. So no need for any coefficients. So this would be obviously our molecular equation here. Our total ionic equation in this case, KCl is a strong electrolyte, so it will break apart into a K plus and Cl minus. Our silver nitrate will also break apart into a silver ion and some nitrate. Our potassium nitrate also strong, so we'll break apart into potassium and nitrate. And as we talked about earlier, it's a solid, so we do keep it together and we do not break it apart. Otherwise, it would not be a solid in this case. And that would be our total ionic equation. Again, there are charges on things, right, and states. Here we can find our spectator ions, so potassium on both sides, identical. Nitrate on both sides, also identical. So those would be our spectator ions. Once again, we're just going to cross out our spectator ions on both sides. And that will leave us our net ionic equation, which would be our silver ion coming together with our chloride to form our silver chloride in this case. Any questions on that particular one there? Taking a look at the next one, we have a positive, negative, positive, negative. So once again, going to be a double displacement reaction. Again, basic unit here, sodium with a +1 charge, sulfide -2. Basic here, calcium +2, and chloride -1. So once again, when we put this together properly and switch partners, we will end up with NaCl, once again, not Na2Cl2, right? And that type of thing. And then when we put these together, +2 -2 gives us a CaS. And based on solubility rules, by the way, that is soluble. Yeah, so I believe so. If we take a peek back at our solubility table there, right there. This is sulfur, which is normally insoluble. One of the exceptions is calcium, which is what we got going on in this case, which makes it not insoluble, but actually going to be soluble in this case. So in this particular example, that's going to be soluble. At this point, we do have our formulas down correctly. We could balance by putting a 2 there. What does this mean for this reaction? Does this actually take place? It does not actually take place, because if you went through the other equations, so if you went through your total ionic equation, for example, after you balanced it, you'll end up with 2 sodium ions plus a sulfide. You'll end up with a calcium ion and 2 chlorides. You'll end up with 2 sodiums on this side and 2 chlorides. And since this is also soluble, you will end up with a calcium and a sulfide. And this would be your total ionic equation, which means, let's see, that's the same on both sides, so they're gone. That's the same on both sides, they're gone. That's the same on both sides, they're gone. That is the same, it is gone. Yeah, there's nothing left. So this really is no reaction happening in this case. Basically, all you got are your sodium ions floating around, your sulfide ions, your calcium ions, and your chloride ions. They're all just still floating around in the solution. No products barely being made in this case, hence there is no reaction action in this case because of that. You basically made 2 soluble things, which just means everybody's still swimming around the swimming pool, right? Nobody got out. Any questions on that one there? All right, one last one here, a little ammonium sulfate and lead 2 acetate. You could just, okay, let's take a look. So here we're starting with some ammonium sulfate. And because it has ammonium in it, that is soluble in everything. There is no exception. We then have lead 2 acetate, which also is soluble in everything because it contains acetate. So acetate is pretty much soluble in everything. Again, if you can't recognize it, it is a double displacement. We got positives and negatives happening here on both sides. Again, when we want to predict the other side of the arrow, we want just the basic units here. So basic units of ammonium is NH4 plus. Basic unit of sulfate is SO4 2 minus. This is lead with a +2. And once again, that is acetate, which a -1. So now when we switch our partners around, we want to make sure we get our proper formulas first. So we are putting -1 and +1 together, which will give us NH4 C2H3O2. And that will also be aqueous, as ammonium, again, is soluble in everything, along with our acetate. I'm going to go underneath here. That's going to put our lead with a +2 and our sulfate with a -2 together, which gives us one of each of these. And that is going to be an insoluble guy there based on solubility rules. And now that we have the right formulas, again, we could balance, and polyatomic ions, just pop a 2 there, and I think you're in business on that. Any questions on that one there? Yeah. Why do you not need around the ammonium and acetate? Is that what you're asking? Yeah. You don't really need it because technically there's only one of them. You only really use the parentheses when you have more than one polyatomic ion. You could if you want to, but typically you don't usually do it if there's just one of those polyatomic ions. Yeah. Other questions? Okay. Questions on net ionic equations, total ionic equations, and molecular equations. Now we've been talking. We also talked about sort of some weak electrolytes. And speaking of acids, let's just talk a little bit about what would happen, for example, if we did have a weak electrolyte sort of involved, and how our equations would look perhaps a little bit different. So if we took something, for example, like hydrofluoric acid, which is a weak acid, and because that is a weak acid, it is also a weak electrolyte, and we react with sodium hydroxide in this case. And sodium hydroxide obviously is a strong base, which makes it a strong electrolyte. This ultimately is still a double displacement reaction. So when we predict what would go on the other side, again, the basic unit here is H plus and F minus, Na plus and OH minus. And we're just going to swap our partners here. And when we do take H plus and OH minus and it comes together, that's basically what's going to form water. So that's going to give us water in this case. And the Na plus and F minus will come together, give us sodium fluoride. And because that does have a sodium in it, we know that it's going to be a aqueous thing. So this would be our molecular equation. It actually is balanced at this point. If we went to our total ionic equation, because this is a weak electrolyte, we actually would keep it together. So we would not break apart the HF as it is a weak electrolyte. And we would then do the rest kind of like normal. This would break apart since it's a strong base and a strong electrolyte, so that would break apart. Water, which is a pure liquid, will stay together. Again, anything that's liquid or solid definitely stay together. And then we would have sodium ion and fluoride here. So this would be what our total ionic equation would look like. And it does affect, for example, how many spectator ions we would have. In this particular case, the only spectator ion in this case is our sodium. So sodium here is the only spectator ion, which we would cancel out. And that will leave us our net ionic equation, which would be our HF plus our OH minus goes to make water and our little fluoride there. And this would be our net ionic equation of what's going on. So again, if you have anything that's a weak electrolyte, you basically just keep it together. And in most cases, you probably will have one less spectator ion because of that. And you basically follow the rest of it the same way. Any question on that there? Yeah. No, I don't believe it is. Yeah, so it will cover just through naming, which I think is that part, chapter 5. Yeah. So this will be like exam 3. So unless you like it on there, because I haven't written it yet. I just throw a few on there. Just write itself. Right now, there's no questions on it. If that makes you feel any better, Hopefully by Thursday it'll be at least a few. I suppose. I suppose that's what Thursday morning's for. I suppose. All right. All right. Other questions on this? All right. So continue on here with our double displacement reactions that we've been talking about. Another type of reaction that really does fall under the double displacement is acid-base reactions. And again, they're sometimes referred to as acid-base neutralization reactions. And when you do take an acid plus a base, you pretty much get two things. You do get an acid plus a base will typically give you, as it shows down there, a salt and water. And basically, a salt is an ionic compound. And again, these do fall under the double displacement sort of big category of types of reactions. So we're basically just going to do our kind of double exchange, and we will form water here. And an acid is anything that has the ability to form H plus ions in solution. And when we talk about acid and bases and acid and base chemistry, something you'll learn if you take 200B is basically these are essentially the same thing. H plus is the hydrogen ions, H3O plus versus the hydronium ions. They basically refer to sort of the acid part of the solution, and they're sort of interchangeable in formulas and equations. We oftentimes will see H plus or H3O plus, and again, it's really just sort of that acid part of the solution. Bases, on the other hand, are things that have the ability to form OH minus or hydroxide ions in solution. And for both an acid or a base, the idea there is they're able to form these things in solution, and they are basically free in solution. So something's a really good acid or a strong acid. It will have the ability basically just to produce just some free floating H plus, not attached to anything, just floating around the solution. And same thing with a base. It would have the ability to form hydroxide, once again, freely floating in the solution, not really attached to anything else, just kind of by itself floating around in that particular solution. Now, as we might have talked about, but just a reminder that there is sort of a list of kind of 6 strong acids, and again, it's a good one to know. HCl, HClO4, nitric acid, sulfuric acid, hydrobromic acid, and hydroiodic acid. So this list of 6 are strong acids, and the reason it's good to know is, well, it'll help you to continue on, but it also is really helpful in this aspect because if you come across something that you can identify as an acid and is not one of those 6, then it's probably a weak acid, which means it's a weak electrolyte. Most weak electrolytes are weak acids and maybe weak bases as well. So that's just by a process of elimination that can kind of help you to know, for example, when you get to the total ionic equation, and you see something like HNO2, which is not up there, you'll go, oh, that's a weak acid, I should keep it together. So just by process of elimination, there's a good list now. Obviously, if it's one of those and you're to your total ionic equation, you're going to break it apart because it's going to be a strong electrolyte. So strong acids and strong bases are strong electrolytes. Weak acids, weak bases are weak electrolytes. A lot of our strong bases, as we might have talked about as well, again, come from kind of group 1 and 2 on the periodic table, and they actually have hydroxide in them, like sodium hydroxide, potassium hydroxide, etc. there. So again, if you kind of go to group 1, lithium, sodium, potassium, hang a right-hand turn at potassium and go to calcium, strontium, and barium. Any of those guys kind of hooked up with OH in the formula will most likely be a strong base. So a lot of our strong bases have OH in the formula and come from group 1 or 2 on the periodic table. Again, if you have any of those guys, again, they would break completely apart there in the total ionic equation. I would say probably your most common weak base is ammonia, NH3. And a lot of organic compounds are weak bases, and a lot of organic ones that contain nitrogen in it a lot of times are weak bases. So, but probably ammonia is probably the most common weak base that you come across. Same idea, obviously ammonia wouldn't break apart since it's covalently bonded, and you would obviously keep it together in that case. So here is, again, a table of some of those strong acids, some of those weaker acids. And again, you can see a lot of our strong bases are that kind of group 1 and group 2, and some of our weaker bases as well. Now, in an acid-base neutralization reaction, especially when you take a strong acid and a strong base, pretty much what's going to happen here, if we take a look at this guy here, or that reaction, I'll just do it up here. We'll do our HCl and our sodium hydroxide. So in this case, we have a strong acid and a strong base. And again, it's still a double displacement reaction because it falls under that category. Going to switch partners, and that's going to give us water. And by the way, in the strong acid, strong base, there are a lot of acid-base reactions. That's essentially where the water always comes from. The H from the acid, the OH minus from the base is pretty much where our water comes from. Circle it. And the salt part basically comes from what's left over at that point, and that's a sodium ion and a chloride ion that will come together. And that's our molecular equation. Again, our total ionic equation in this case would be H plus and Cl minus, as that's a strong acid, so it'll break apart. That's a strong base, which means it will break apart. Water, which is a liquid, will stay together. And our sodium chloride, which is a ionic salt, will break apart as well. And if we look at our spectator ions, we got chloride on both sides, we got sodium on both sides. Those guys go away. And our net ionic equation is really what's happening here. It is, again, that H plus from the acid coming together with the OH minus from the base to make our water. And again, if water formation is one of the 3 reasons why a reaction takes place, and that ultimately is what happens in any combination you would like to choose of a strong acid and strong base together. So if you take any strong acid, strong base together, and you get all the way down to the net ionic equation, you always end up with basically water being formed, and that is the ultimate thing that's happening here. Again, why it is called a neutralization reaction, because basically you're just forming water in this case, and that's what happens. Any combination, strong acid, strong base, will end you there. We just did one again with a weak acid, which will be a little bit different, obviously, and you'll have, again, that weak acid still left over because it will not break apart. Any questions on that there? Now, there are some reactions that actually will be a double displacement reaction, but will actually produce a gas as a product. So that does occur. And a couple of examples of that, let's take a look at a few of these examples here. Good looking. Let's take a look a little longer. So again, here we have a double displacement reaction, positive, negative, switching partners here. And this produces a gas directly from that exchange, and we produce here some hydrogen sulfide gas in this reaction. So this is a direct just swapping out of our ions and forming this gas. Other reactions will actually form a gas as a result of the double displacement, followed by a second reaction, which is a decomposition reaction. So what happens in that particular case is one of the products that are formed as a result of the double displacement reaction will very quickly just decompose into a gas. And that's what we see here. If we take this and this guy, again, switching partners, we will form this H2SO3, which is sulfurous acid. And sulfurous acid will then go through a decomposition reaction really quickly and will produce water and some sulfur dioxide gas. So it's kind of a double displacement followed pretty quickly by a decomposition reaction. Kind of like when you put some sodium bicarb or baking soda on an acid. So if you take like some HCl and react it with a little bit of sodium carbonate or sodium bicarbonate, again, you get a double displacement happening here, and we end up with H2CO3 and a little sodium chloride and some balancing here, maybe like so. This carbonic acid will decompose super quick into water and CO2, and you would see that kind of fizzing, pop, pop, fizz, fizz. Like when I put the baking soda on some acid spill in lab, you see it start fizzling up and stuff like that. So that will happen really quickly. So here's a table that sort of works through kind of your double displacements that could lead to a gas being formed. So if we take any type of metal that has sulfur or hydrogen sulfide in it, you will then produce, with a reaction of an acid, that H2S gas directly, and it will be formed. If you have a metal with any type of carbonate or hydrogen carbonate, you will form what I just did in the last example, some carbonic acid, which will definitely go through a decomposition and form some CO2. That was the other example, the one that we had in the problem there. It will form H2SO3, which will also go through a decomposition reaction and secondarily produce SO2. And lastly, ammonium, NH4 plus. If you react it with a base, will make ammonium hydroxide, and it will decompose into ammonia gas in this case. So those are sort of indirect formation of a gas, basically a double displacement followed directly by a decomposition reaction. Any questions on that there? All right, so the next type of reaction we're going to talk about is what we talked in depth about a little bit last time, but we're going to kind of tie it into kind of what's in the chapter and kind of classifying reactions. So remember that double displacement reactions can more specifically be classified as precipitation reactions are acid-base reactions, and really double displacement reactions, as we've been talking about, handle the two reasons why a reaction takes place, or two of the three reasons, is the formation of water, like we saw there in the acid-base reactions, and the formation of a solid, like we see in a precipitation reaction. Now, the rest is pretty much going to be our electrons being transferred, and those are our redox reactions, as we talked about. And redox reactions involves electrons being transferred. And again, you can think of redox reactions as the big category of reactions, kind of like double displacement is for precipitation and acid-base. Redox is, again, the big category for all the other types of classifications that we talk about in terms of reactions like decomposition, single replacement, and so forth. Here again, as we talked about, oxidation has several definitions, but in here, usually it means that you will lose electrons. Reduction means that you will gain electrons. And remember that you could look at the oxidation number to sort of figure out what's going on. And you can use a basic number line to help you decide, is something going through oxidation or reduction? So if you look at its oxidation state of something on the left-hand side of the arrow of an element to the right-hand side, the same element, and it is getting more positive, that means that that substance is going through oxidation. If you look at the oxidation number on the left-hand side of the arrow of an element to the right-hand side of the arrow, and it's moving in this direction, the more negative direction, it means that that thing is going through reduction. So again here, if we look at magnesium here, that is 0 because it's by itself, not attached to anything. It is a +2 over here on the right-hand side. And we see magnesium starting at 0, ending at +2, becoming more positive, and that is why that again is referred to as the oxidation half reaction. And remember that in an oxidation half reaction, we have electrons on the product side. So that is I tell that that is an oxidation half reaction, like they are being given off. In this case, we actually have 4 electrons because each magnesium will lose 2, and in the balanced equation here, we have 2 magnesium, so that's a grand total of 4 electrons being moved. Oxygen over here on the left is 0. On the right, that is -2. So when we look at oxygen, it's starting at 0 and ending at -2, which means it's moving in the negative direction on the number line, and it is going through reduction. We also know that this is the reduction half reaction because we see our electrons on the reactant side of the molecule. These are called half reactions because if we add these together, as we talked about, the electrons should always cancel out, right? And that sometimes requires us to multiply the half reaction by a number. And then everybody on the left stays there, and everybody on the right stays there. And since those are 2 ions, they will come together and make an ionic compound of magnesium oxide. And that will give you your overall reaction of 2 magnesiums plus oxygen makes a magnesium oxide in this case. Any questions on that there? Remember as well, we talked about, get rid of that there, I think. We also talked about oxidizing agent. And remember, the oxidizing agent is the substance that gets reduced. And we also talked about the reducing agent. And the reducing agent is the substance that gets oxidized. Kind of opposite of name. And the reason for that, again, is that is what it is causing to happen in the other thing. So in this particular case, our magnesium is getting oxidized. It is the reducing agent. When magnesium loses its electrons, it allows oxygen to gain them and get reduced. So it's causing oxygen to be reduced. The oxygen here is our oxidizing agent. In order for oxygen to gain electrons, it's got to cause somebody else to lose them and get oxidized. So that is known as the oxidizing agent. So remember that if you are asked that question of what is being oxidized and what is being reduced, that is a different question than what is the oxidizing agent and what is the reducing agent. So again, those are different sort of questions. By the way, what is being oxidized and reduced? And what is your reducing agent and oxidizing agent should always be found on the left-hand side of the arrow. The reactant side is where you'll find all those guys. Any questions on that there? So in later chapter in this book in 200B, you'll talk about electrochemistry, which is this. But what is happening in this particular case is a oxidation reduction reaction. So what we have here is in this solution here, there's some copper ions floating around. That I believe is solid zinc. And once again, where you find ions are in solution. So in this particular case, what happens is the zinc will lose electrons. And when it does, it actually will jump off the solid and go for a swim as zinc with a +2 charge. When it loses those electrons, it will send them over to the copper, which will pick up the electrons and go from copper with a charge to solid copper. The copper will jump out of the pool onto the stick there, and that's why you start to see that discoloration sort of happening. That is coming out. You also might notice that the solution here to start with is blue, which is reminiscent of copper being present. And as this reaction continues, the solution in that beaker is not so blue anymore, right? And that's because all the copper ions jumped out of the pool and onto the metal that's there. All the zinc guys, which are colorless, jumped into the pool, and we actually see a change in color that's happening here. So this is a redox reaction that's happening when you do something like a galvanic cell or build a galvanic cell. That is basically what's happening, these transfer of electrons. So if we take a look at this, zinc plus our copper 2 sulfate goes to zinc, sulfate, and copper. We can see what's happening here. This is a redox reaction. If we take a look at our oxidation states, again, zinc is 0. This is copper 2 sulfate, which means the copper has a +2 and the sulfate is -2. The zinc here is +2 and the sulfate is -2. And the copper here is 0 on the right-hand side. So we can actually see what's happening in this case. We can take a look at our number line. And if we take a look at the zinc on the left, it's starting at 0. And on the right-hand side, it is ending at +2, which means in this particular case, the zinc is actually being oxidized. It's becoming more positive. So this guy here is being oxidized. But remember, as we talked about last time, if you're able to figure that out, by default, the copper here will be reduced. And I know that as well. We could go to our chart. Copper starting on the left-hand side at +2 and ending on the left-hand side and ending on the right-hand side at 0, heading towards the negative side, which means it is going through reduction. And that would mean in this particular case, the zinc is our reducing agent and the copper 2 is our oxidizing agent in this case. Again, opposite of what is occurring. Now, to fully understand what's going on in this reaction, we could also write our 3 equations like we did with double displacement reactions. We obviously have our molecular equation here. This zinc is a solid. This guy is an ionic compound that will break apart into copper 2 and sulfate. The zinc sulfate will also break apart into zinc and sulfate here. And our copper will stay here as our solid. So this would be really our total ionic equation for this redox reaction. Is that right? Lovely. Hopefully the roofing tiles will hold. All right, so this is our total ionic equation. Sounds like this morning when I was teaching, the same thing happened. I was in the middle of teaching, like, everybody's looking like, is that the rain? Like, I hope so. When we look at our spectator ions in this case, though, we actually only have our friend sulfate is the only spectator ion. Now, why is zinc on the left and zinc on the right not a spectator ion? Because the zinc on the left is not an ion. Yeah, there's no charge on that. That is solid zinc. That is different than zinc. Guy on the left is like in that picture, the solid piece of metal hanging in the beaker. The zinc on the right is the guy swimming around at the end in the liquid part. Yeah. So those are two different things, even though they're both zinc and they're by themselves. One has a charge, one does not have a charge. They are not ions, both of them, and they are not spectator ions. Same thing with the copper there, right? The copper on the left has a charge. He's swimming around. Guy on the right has already got out of the pool for the day, right? And he's on the metal piece there. So in this case, the only spectator ion we actually have is our sulfate. And that would be the only one that would be canceled out. And this will get us our net ionic equation that's happening here, which is our zinc plus our copper 2 goes to zinc plus our copper. And this is really what's happening in this case. What's happening in this case is this zinc that has no charge decides, hey, I'm going to give up a couple of electrons to you, copper, with its charge. And the result of that is because the zinc gave away 2 electrons, it now becomes positively charged. And the zinc picks up those, the copper picks up those electrons and now has no charge. And this is our electrons being transferred. And this is ultimately what's happening here. So you could also write total ionic equations and net ionic equations for these type of reactions, redox reactions. They're a little bit different, but again, works the same way. You also will probably have only one spectator ion, usually in this case. By the way, just to reiterate again, as we might have talked about last time, but in double displacement reaction, there are no electrons being transferred. The charges that are on both sides stay the same, so nothing really changes on those type of reactions. So there is no like redox happening with any type of double displacement. So if we take, for example, this guy, which is copper wire, which would just be solid copper, reacts with silver nitrate, which is AgNO3, to form silver metal in this case. We really don't even need the other, but it is copper 2 nitrate, by the way, in case you wanted the other thing there to answer this question. And I would say in most cases, solid copper will end up as copper 2 floating around in solution. That's very common, is what it will end up as. We could also balance it by putting a 2 there and a 2 there. But to answer this question, we want to know really what is the oxidizing agent in this reaction. So we could look at our oxidation numbers. So our copper here is 0, our silver is +1, -1 for our nitrate, 0 for our silver, and really +2 over here. But even if you did not know this guy, we will just look at the silver to help us answer this. So if we just look at the silver, perhaps you're not sure about the other guy that's being formed. Silver on the right-hand side here is +1, which is about here. On the left-hand side, it is ending up as 0, which means the silver in this case is becoming more negative and being reduced. And that means by process of elimination, we know the copper here should be oxidized. Yeah. And by the way, we see that with it going from 0 to +2 in reality, it is becoming more positive. So it's going through oxidation. That would mean here in this case, my oxidizing agent would actually be the silver over here, the silver nitrate. And really it's the silver ion, the Ag plus is really the oxidizing agent. And our reducing agent in this case would be the copper. Any questions on that there? So we did go over this pretty detailed the other day, so I'm not going to go spend a lot of time on, again, assigning oxidation numbers because we did it, I think, on Thursday. But a reminder, just general rules and ways to do it. Anything that's, again, by itself, not combined with anything else, will have an oxidation state of 0. If it is an ion that has a charge, then whatever the charge is its oxidation number. Oxygen, as we talked about, is usually a really good place to start with. And again, in most cases, it's going to be -2, except if it is peroxide. Again, remember that is -1. And if it is peroxide, again, that extra 2 kind of hangs out there that we see, you know, kind of over here. We kind of see that extra 2 as well. We also talked about the oxidation state of hydrogen is typically +1, unless it's sort of a hydrogen that comes after a metal, then it'd be like hydride, which would be -1. Everybody in group 1 and group 2 will be +1 and +2 respectively, and fluorine is always -1. Remember that when we do add up all of our oxidation numbers, they do need to equal the overall charge or whatever it may be. And if it does not have an overall charge, then they need to add up to 0. So I believe we did all these last time, but I'm just going to go through this one more time just to reiterate how to do it. Again, I would start with oxygen, which is -2. That gives me basically a -6. Go to the left there, which is hydrogen, which is +1. A reminder that if you got kind of like a 3-pack of elements like this, kind of save the one in the middle for the end is usually the move. This has an overall charge of -1, which means when we add that together, we have a -6 and +1, which is a -5. That means that in this case, the carbon would has to be +4, and that would leave me an overall -1 charge. Also, a reminder that when you write oxidation states or numbers, you should include the plus or minus, and you should give it for the one element by itself. So oxygen here would be -2 and not -6. So that would be the proper oxidation state there for the oxygen. Any questions on that one there? Here again are some common oxidation states of things, and a lot of those transition metals could have different oxidation states. And you can see something like Mn, for example, has a lot of different oxidation states. And the other thing that we also talked about when we talk about oxidation numbers and states is, again, a reminder that if you are dealing with an ionic compound, then that element will probably have the charge or oxidation state that you think of. But remember that if we're dealing with a covalently bonded sort of element and an atom, based on what is bonded with and who is sharing electrons and electronegativity of those elements, things that we normally think about as being negatively charged, for example, can end up with a positive oxidation state. Again, for example, here, chlorine. We normally think of it in an ionic compound where it is the one receiving the electrons, it will be -1. But if chlorine's in the middle and it's got a lot of electronegative atoms around it, it's going to have early its electrons kind of sucked away from it, and it's going to actually end up with a more positive oxidation state, like a +5, for example, +4, whatever it may be. So a reminder again that sometimes people have a hard time with that because they get beat in their head like these are the charges for naming for all these things. And again, in this situation where we're talking about oxidation numbers and states, it is definitely possible in a covalent situation that something we normally think about as being negative will have a positive oxidation state. Any questions on that there? And just an example of that would be probably somebody like this guy. We took a look at this one that we did last time as well. Again, here we would start with our oxygen, which is -2, and that will give us a -6. Our sodium is group 1, which means it will be +1. This is going to equal 0. And again, to get us to 0 there, we got -6 and +1, which means we have -5 left over. So our iodine, which we normally think about in an ionic situation as being a negative charge or -1 charge, in this situation, because it's sharing electrons, we'll actually end up with a +5. And where it's sharing electrons with is really not the sodium, because this is an ionic compound. It is this sharing of electrons between that iodine and those oxygen atoms. Oxygen way up there, right? A lot further up than iodine is. More electronegative, going to suck the electrons towards the oxygens, making this more and more positive again in this situation because they are sharing electrons. So again, those are things you want to think about. Any questions on that there? Okay. So now we're going to talk about more specific ways of classifying redox reactions. And again, these are all redox reactions that fall under that umbrella. The first one's a combination, and is sometimes referred to also as a synthesis reaction. And in a synthesis reaction, basically two things make one thing. So kind of putting things together is the way you could recognize that. Two things make one thing. And that's what we see here. Two things make one thing, and that's definitely a synthesis or combination reaction. This is still a redox reaction. So if we take a look, that is 0, that is 0. That is +3, and that is -1 in terms of our oxidation numbers. So our aluminum is being oxidized like we would expect because it is the metal. It's going to lose electrons. Our non-metal here is going to pick up those electrons and be reduced in this case. So it is overall really electrons being transferred here, but most people would probably classify this as a synthesis or combination reaction. as a more specific way of classifying it, even though, again, it is still a redox reaction. The next type of reaction is pretty much the opposite of that one. And that's basically you got one thing and you're going to break it apart into multiple things. So one thing becomes multiple things. So it's kind of the opposite reaction. That is what we see here, potassium chlorate, potassium chloride, and oxygen. And again, one thing makes multiple things. We saw that in what we talked about with the gas formation, like we make carbonic acid, breaks apart into CO2 and water. Again, a decomposition reaction. Still a redox reaction. This is -2 here for our oxygen. That's -6, +1 for potassium. The chlorine here is starting with a +5. On the right-hand side, we do make an ionic compound, which is +1, -1, and 0. So if we take a look at this once again on our number line, our chlorine is starting at +5, which is over here, and on the right-hand side, ending at -1. So it is going all the way to the negative side. So it is the chlorine here that is getting reduced. And in this case, it is not the potassium, it's just a spectator ion. It's the oxygen here. That's the opposite thing that's happening. Oxygen starting at -2 over here on the left and ending at 0, becoming more positive. So it's actually the oxygen that is getting oxidized, yeah, as you go through that. So still a redox reaction, but more specifically called a decomposition reaction because it's one thing that makes multiple things. Any questions on those there? There we go. Now, a combustion reaction is another redox reaction. And although when most people think of a combustion reaction, they oftentimes think of an organic combustion reaction, which is an organic compound like carbon, hydrogen, and oxygen, kind of like what we talked about when we did the combustion analysis, when we did the empirical formula, right? So we took that guy, we had a little O2, CO2, and water. So if you got an organic guy and O2 on this side, it's pretty safe bet you're going to make CO2 and water, and that's a combustion reaction. For example, that's what happens when you light your Bunsen burner, right? A little methane, some oxygen, a little spark, you have CO2 and water that's basically be made. Now, a more generic sort of definition of a combustion reaction is pretty much all you need is that guy right there. So all you need is basically oxygen to be involved there on the left-hand side of the arrow, and you could classify it as a combustion reaction. So that's what we see here, oxygen, combustion reaction, combustion reaction, combustion reaction, still redox reactions happening here. So these guys are still redox, 0 and 0. -2, that gives me -4, +4 here. So on this case, our sulfur is going from 0 to +4, becoming more positive, going through oxidation. And our oxygen is starting at 0 and ending at -2, becoming reduced in this case. So still a redox reaction happening here. Same thing down here. We got 0, 0, +2, -2. Again, the magnesium becoming more positive, going through oxidation. The oxygen becoming more negative, going through reduction. So a redox reaction. And also a combustion reaction. And for the trifecta, right? Dare I say it? I see redox reaction classification. I see combustion reaction classification. And dare I say, it looks kind of like two things make one thing. Could be a synthesis or a combination reaction as well, right? So there are multiple ways you could classify the same reaction depending on what you're looking at. So it does sort of, there are multiple ways to kind of do that. So this particular one could be kind of classified 3 different ways depending on what you're sort of looking at. Any questions on that one there? Yeah. You can't see it, it's because it's so hot, it evaporates, right? So don't do this, but actually some schools do this as an experiment to talk about that. If you light a Bunsen burner and you put it onto the bench, which is cold, you'll actually see condensation occur. Yeah. And that's the water cooling down because it hits something really cold. You'll see that kind of condensation. and that's the water. I'll show you that it's there. But when you light in it, it's just so hot right there, right? You're not gonna be able to see it. It's just gonna evaporate basically. It's kind of up in the air. Yeah. Other questions? Next time you have a Bunsen burner lit, don't do that in our class. Yeah, do it in somebody else's class. All right. The next type of reaction that falls under redox reactions are single replacement reactions. And single replacement reactions have this sort of formula. It can be this guy, which is a metal and an ionic compound. And these are very much like those reactions we did in that very opening sort of experiment, maybe experiment 3 or 2 or one of those. Actually, experiment 3, I think. And if this is a metal, it does not have a charge to begin with, but it will come in and kick out the positive guy and make a new ionic compound, and this guy will come out with no charge. And you could also do that like we did with those halogens, where this is a non-metal to start with, no charge, positive, negative. It would go kick out the negative guy because non-metals normally make a negative charge and make a new ionic compound. And this guy that gets kicked out has no charge. So these are overall referred to as single replacement reactions. And in order for this reaction to actually occur, whatever is coming in, so whatever this is, needs to be more reactive than what it is replacing. And if it is not more reactive, then the reaction will not take place. So even though these are classified as basically single replacement reactions, which are redox reactions, you could even go a step further and subclassify the single replacement. This is known as a hydrogen displacement because this guy is going to come in and kick out the hydrogen. When hydrogen gets kicked out by itself, it makes hydrogen gas, some bubbles, and all that good stuff. This is a metal displacement where the metal will come in and kick out the other metal. And this is a halogen displacement where the two halogens will replace partners. Again, this is still a redox reaction happening. This is 0. This is -1 plus 4, 0, and +2 and -1. So here the magnesium is going from 0 to +2, which means it's being oxidized, becoming more positive. The Ti here is going from +4 to, not there, where'd it go? +4 to 0 is becoming more negative if you follow the number line. +4 going to the left-hand side, becoming more negative, is being reduced. Same thing for all of those. So these are all redox reactions. They're all single replacement reactions. How do you know whether or not a reaction will take place? You could use what is sometimes referred to as an activity series. This is a pretty detailed activity series. A lot of times it's just the elements listed and hydrogen somewhere in the middle. And typically when you look at an activity series, anything that is higher up on the list can replace somebody lower, and anybody lower on the list will not replace anybody higher on the list. So if you have just a basic sort of activity series, again, anything higher will replace lower, and anything lower will not replace anybody higher. So for example, if you took zinc plus your hydrochloric acid, this reaction would take place and you would get the zinc coming in and kicking out the hydrogen and making zinc chloride plus the hydrogen gas. And in this particular case, a little balancing. Now, if you try this exact same reaction with copper and hydrochloric acid, this reaction would not take place, again, because copper is less reactive than hydrogen, and it would not take place. You can kind of maybe see it on this list here. We can find hydrogen. There is copper lower on the list than hydrogen, and again, we could find zinc higher on the list than hydrogen, so it will replace it. As you can see here, calcium plus water. If we find calcium on the list, it will react with cold water to produce H2, so this reaction will take place. If you look at lead and you try to use cold water, lead is not going to work with cold water. It actually needs an actual acid to be a little bit stronger to actually make that reaction occur, so that reaction would not take place. So I would say, though, a basic sort of activity series is just kind of that listing of elements. And again, higher will replace lower, lower will not replace higher in that type of single replacement reactions. Any questions on that? And we actually did the halogens when we did that experiment. If you remember when we did that experiment with the different layers where the colors changed from the top layer to the bottom layer and so forth, we found that reactivity, right, in group 7 increases as you go up, right? So fluorine is more reactive than chlorine. Fluorine would replace chlorine. Chlorine would replace bromine. Bromine would replace iodine. Iodine will not replace any of those because it's the least reactive. So most reactive, least reactive in that case. And that's why when we look at this one here, this guy will definitely replace because chlorine is higher on group 7 than bromine. This one will not take place because iodine is lower in group 7 than bromine. These again are still redox reactions that are taking place. And to finish up here on this chapter, it is possible for both reduction and oxidation to occur in the same element at the same time. So it is possible the same element will actually be oxidized and reduced in the same deal. That is what is known as a disproportionation reaction. Basically, both are happening at the same time. So let's take a look at this one. Here we have our chlorine over here, which is 0. On this side here, that's -2, -1. That means here this is +1 for our chlorine. This chlorine is -1. So what's happening in this case is that chlorine is going to this, and that chlorine is also going to this. The same chlorine molecules are both being oxidized and reduced. In the case of the first one, it's going from 0 to +1, so it is being oxidized in this case. In the case of the second one, it's going from 0 to -1. It is being reduced in this case. So it is possible for the same element to both be oxidized and reduced in the same reaction. And again, that's what's known as being a disproportionation reaction. It usually occurs with chlorine a lot of times. That's very popular in atmospheric chemistry. Any questions on that? So again, just to summarize, we won't go through these, but we have our redox reactions, which is our electron transfer. More specific classifications are synthesis, combination, decomposition, single replacement, and combustion. We have our big category of double displacement, which has no oxidation reduction happening. And in that category, we have more specific precipitation reactions and acid-base reactions. And again, double displacement takes care of water being formed in solid. Redox reactions take care of electrons being transferred. Any questions on any of those there? So again, we've got an acid-base, single replacement, combination, synthesis, redox there on the bottom of those. All right, that wraps up this chapter. We also will, again, on the following Tuesday, we will have a visitor coming to our class, yes? So I'd appreciate if everybody's here on time, yes, pay attention and all that good stuff. I appreciate it, yeah. To watch me, I'm just gonna do some comedy for a while and then they'll get tired and leave, I imagine. But yeah. So that is the following Tuesday. So. All right, so if you missed on the roll sheet, make sure you do. I do have your quiz